actually picking my voice up? Not very well. Is that better? Fairly. Okay. There are insomniac women all over the web. This is a different picture from the one we saw last week. I was quite interested to notice that although there are pictures of men lying awake, it's never with a clock. And I don't know why that is. It's only women who wake up and look at clocks. If you do suffer with insomnia, the advice is not to keep checking the clock. You should not see how much longer you have during the night to sleep. In fact, put the clock somewhere else where it might alarm at the right time if you don't want to be watching it. So let's go back to this experiment we looked at last week. And I posed this question in a slightly different way. I told you last week that I gave my insomnia treatment to 10 people, and half of them said they slept a bit better. What I asked you last week was, how do you set this experiment up? What I want you to tell me instead is, what's wrong with this experiment? What's different about it? Okay, so sample size is a bit minimal here. And what else? You don't know the... Oh, that's interesting. So this comes into the question of patient stratification. The suggestion was we don't know what else is wrong with the patients. It's certainly true. When I asked the 10 people to take the drug, I didn't say to them, do you smoke? Do you have high blood pressure or anything like that? So we might need to know more about the population. So that's the stratification.
You could even have a shift worker in there who's trying to sleep during the day.
Yes, that's true. You might have people who are accustomed to lying awake at night. So you would want to know more about the diagnosis of insomnia. You'd want some reliable measure that these people really do have a problem. Because after all, if they said, oh, I don't always sleep very well, that might not be clinical insomnia. That's a good point. So sample size, and then what else? Think. Sorry?
How do we measure the
Yes. How do we measure the outcome? So we need a good outcome measure. Because telling me that you slept better, that might be good news for you, but I need to know how much better you slept. I gave them a drug. What else might I have given them? There are some of them. A placebo, or can you see an ethical problem with that? If this wasn't a sleep trial, but say a trial for HIV, would it be ethical to give some people the treatment and some people a placebo? So what would I give the other people instead of a placebo? Okay, other drugs, previous drugs, best available treatment. So you would have a placebo or best available treatment.
Ben Goldacre has raised this as an important ethical issue in terms of how pharmaceutical companies organise their trials, and that some of them will test against a placebo, knowing that their drug is more likely to look useful in that type of test, so they're more likely to have a foundation to get on the market. That's purely an attempt to manipulate what's their commercial outcome.
Yes, it might be easier to show that your drug is better than a placebo. It's harder to show that your drug is better than the current standard drug. A point that I think was implied in one of the earlier contributions, but not really brought out, is that we don't know the characteristics of these 10 people, but we would perhaps like 10 people who do not suffer from insomnia. We would like to know that our drug is having a specific effect on people with sleep problems. My shorthand for that would be a control sample. So a control sample is people who do not have the condition that you're trying to treat. So as well as having a controlled treatment, placebo, or best available drug, you might have a control sample. You don't always do that, but you can see that it would increase the power of your studies if you did do that. So you told me about the size, and I think you called things like the size, perhaps a control sample, you need a reliable outcome measure, and we need a controlled treatment. What else though? I mean, did I have a very well-defined question when I gave them this drug? I just said, here, take this and tell me whether it's good.
Randomization of treatment.
Oh, randomization is one thing, yes. With very small samples, that's difficult. Because you might randomize by flipping a coin. So 10 of you here are going to take my drug. If it's heads, you get the treatment. If it's tails, you get the placebo. If you've only got 10 people, it's quite likely it will come up heads every time. So you have to find better ways than that of randomising if it's a small sample.
Indeed, in this situation, it would probably be best to pair people into best matches and then randomly decide between each of those.
That would be a good design if you have small people and you want to get maximum information. But what... So randomisation is one thing I like to do. And of course, with these 10 people, I know that they've all got the treatment, so that's bad. I want to be blind. I want not to know who has got which treatment. But what else? I mean, I asked them, tell me if you sleep better. What could I ask instead? Or what could I ask myself?
When I was talking about the weak hypotheses that are relatively uninformative if you get when you test them, there are a very general possibility that the drug will have some effect.
Significant
Hypothesis.
Well, let's say I didn't give them a drug. Let's say I gave them, my drug that I've been developing, I tested in the lab on animals. Let's say I gave them something like chamomile tea, and I said, oh well, there is some folklore that this helps me to sleep better. I can't turn that into a very strong hypothesis. Whereas if I've got this drug and it's cost me millions to develop it already, I'd better have some idea of what I expect it to do. So what could I ask about this drug and its effect?
At specific time, usually 1 hour, 2 hours more.
Okay, so I could say, based on previous studies, perhaps in animals, that it improves sleep by perhaps 10% of your nightly sleep.
Or indeed in the drug company example, it might be how much of an improvement you need for it to be actually worth taking it forward to market. It's going to cost you more to take it forward further.
It might work perfectly well. It might reliably improve your sleep by 10%. But if you normally sleep only 4 hours a night, that's 240 minutes, you might not think that an extra 24 minutes was worth having. So you better have a hypothesis. You better say what you expect to happen, because it is far more powerful to test a strong hypothesis. My hypothesis is that this improves a certain phase of sleep, or if it improves it by 10%, or if it improves it by 20%, that's better than saying it will have some effect on sleep.
Indeed, making you sleep worse would be verified if you were to just say it will have some effect.
Yes, it would be easy to test the hypothesis that it has some effect. And if it made some of the patients worse, then it'd be easy to prove the hypothesis. And you can see how those things give you a more sophisticated experiment than just asking that. Tell me what you felt like. So, okay, you came up with some of the examples that I anticipated. So the sample was small, and then controlled treatments, either something that we know makes people see better, or something that we have no reason to think will be better. And I underline things I think are most important. One is sample and science, hypothesis, and pressure, and control. All these other things matter as well, particularly in clinical trials, where there's money, insurance issues, and people's health. But for any experiment, you really do need to have a sample, and you have to think about its size. You need some controls, some idea of what you expect to see, and a prediction. You need a way of measuring it. So think about that. Sample, controls, outcome measure, hypothesis. There's probably a lot that people make up of that. Shock or something. I'm not going to dwell on this slide, which I'll put up on the website, but with a sleep trial, the gold standard would be something like a randomized controlled trial, and Bradford Hill in 1940 is credited with devising the randomized controlled trial. And Bradford Hill has also given his name to the criteria that you use in an experiment to determine whether you have a causal effect or not. Very often in science we see associations between things. The example I like to give is that as I get older, the national debt increases. Right? That is true, but my getting older doesn't cause the national debt. Bradford Hill had a list of criteria for deciding whether your intervention caused the effect of disease. And there are all kinds of other designs you can use for increasing sophistication. And I'll put these up on the board with a note about them. But the design you have seen, or the one that we told you we might have, is the parallel design, where there's treatment or control. Joanne said to the Friday group last week that you could have a crossover, so that the people who had received one intervention would then receive the other one later, to see whether the effects were consistent. The cluster is something you perhaps do with schools, prisons, villages, families that are already pre-formed. You're not randomly selecting intervals within them. But in published trials, 80% of randomized control trials are parallel, so that's where you have treatment or control. It's important to know about randomized control trial because you won't do one as an undergraduate, but there's a gold standard for experiments, and we can import some of the disciplines of randomized control trials into laboratory work.
It's within the realms of possibility for some of them for finding a problem. Probably not this group, but perhaps some of the nutritionists would like, but the problem there is very small sample sizes.
And quite often you might be doing a retrospective trial where you look at people who have equal certain food studies and then find out what had happened to them. Randomized control trials are usually prospective. You give the treatment and then see what happens.
There are even a few of those trying nutritional supplements and then taking physiological measures.
Okay.
But as I say, the issue is that they will generally be pretty small sample sizes. It does mean that they need to do their designs pretty well if they're going to get anything useful out of it.
Any meaningful data and really reasonable sample sizes. Yeah. And again, I'll put this up, but the randomized control trial is considered good evidence of effect if you're looking at drugs. And then there are these other levels. For example, personal observation is not considered good evidence. Expert opinion is not considered good evidence. Think about that when an expert is talking on the radio about obesity or cancer or the effect of watching videos on children's attention. You know, the expert may be expressing an opinion, might not be actually summarising the field fairly.
And Stephen Jones has recently noted that the BBC particularly is prone to the phenomenon where they feel that because they're the national organisation they have to be balanced. And so you will often have someone who is really an expert giving an opinion, and while you would ask them to even question that, they will then have someone from the Green Ink Brigade to give a balance, and the two will be given equal weight in the interview.
Although there may not be equal scientific credibility. And although these things are designed for drug trials, again, there are, I think, habits of thinking that come from all these kinds of study that we can import into the laboratory. I would say that all of these can be adapted to laboratory studies. saw a slide like this last week, and before you get this into your head, what a simple experiment can often be thought of as if then. If I do X, Y will result. X is something that you, in a sense, select or manipulate. So we'll see some examples in a minute. And Y is the outcome. And in the sleep example, and you can think about this if you're stuck and you can't get this clear in your head, if the drug is administered, the patient will sleep better. You know, that's rather a weak hypothesis, but that's the way that this experiment has been thought of.
Anyone got a hammer?
Okay, so thinking about what you told me earlier, thinking about the previous slide, tell me again what you need for a minimal experiment. What are the things you need to keep in mind if you're going to do these intensive experiments? Like say, the effective drug and sleep. I'm thinking more of the things you need to assemble or think about at the outset. I'm not really thinking things that can go wrong. Though you're right, and we're talking then about protocols.
Yes, indeed, because you need to be thinking about how much variability you're going to get both from you not being able to prepare well and the natural variability in the sample. That does come into the thinking in the assembly in terms of how large a sample size you're going to need.
So, okay, that does address the question of sample size indirectly. So what else apart from your samples you need? What are we going to do with our samples or our populations? What are we going to do with our patients? To do an experiment, what do we need to administer to the patients? We need a drug or some treatment. So the first thing we need is sample, and it had better be a big enough sample, and we need some kind of treatment. And then what do we want to know? Okay, how would we measure now the results of the treatment? We could ask some questions. What would be better than asking them questions about the results? Oh, well, that would be a sophisticated way if we were looking at the MRI to see what happened during REM sleep. But at all events, what do we need to know about their sleep patterns after we've taken this drug? Or what do we need to know about the quality of their sleep? Okay, and how would we measure that? What would be the easiest way of measuring that?
Well, the easiest or lowest power is to ask people to report.
And so that's what I initially did. I asked them what they felt. And then we decided there was a better way of doing it. Okay, so we need some outcome measure. So we need a sample, we need a treatment, we need an outcome measure, and then what was the thing we were just talking about now? About the question we asked. We need a hypothesis. And it better be a strong hypothesis if we want the best outcome.
Indeed, I was the hypothesis to really come first.
I was thinking about this when I came to the lecture. I thought, how am I going to motivate this? Because I can certainly think of experiments I've done where I had an idea, and then I thought, how do I approach this? What kind of sample can I get? You know, do I need patients, student volunteers? Do I need to use invertebrates? Do I need to use my colony of mice? And I do cell culture. So you sometimes have a hypothesis, and you think about the sample afterwards. But very commonly, particularly if your lab has had a legacy of experiments over the years, you have a system that already works. You already grow cells. You already put mice in the maze.
Indeed, this is often the foundation to a successful research effort, that you've got something, that you or the lab got something going which is working, and
You mine a rich seed.
mine a rich seed.
So So, yes, you might start with the hypothesis and you might start with the sample, and both things happen in practice. So, sample, treatment, some outcome measure, and a hypothesis. Okay, so you told me there, those are 4 things I would say. I haven't actually stressed hypothesis there, but I have stressed control.
Yes, well, yes. I would say the structure of your test would come from the hypothesis.
Yes, that's true. I mean, what you choose to measure will be influenced by what you expect before you do the experiment. That's a version of the previous slide. Alright, so let's think about a controlled experiment in the science lab. These are cells growing in culture. These are cells growing in a 24-gram plate. The medium is pink because it has a pH indicator. And we grow these in an atmosphere of carbon dioxide. So these could be any kind of cells. They could be primary cells that have just been taken from a patient or an animal. They tend not to survive in culture. They're probably a cell line. Cell lines they're often called immortal. They do in fact die in culture after a number of divisions. But they're cells that you can keep alive for a long time while you do biochemistry, pharmacology, molecular biology. Cell biology is the basis of lots of science. So here's something to think about. I've got a cell line which secretes amyloid peptide into the pink medium. And this cell line dies. We presume it dies because it's secreting this amyloid. And we also have a fact about a protein called clusterin. Clusterin is elevated in Alzheimer's disease. That's relevant because amyloid peptide is supposed to be the basis of Alzheimer's disease. The reason why people with Alzheimer's disease is the reason why their brain cells die. So here we have 2 facts about Alzheimer's disease. One is that amyloid peptide is involved, and I've got a cell line that produces amyloid. And I also know that there's this stuff called clusterin, which is increased in the brains of amyloid patients. So I have these cells, and I've got a clusterin antagonist, which I've made up a name for. I've called it cluster buster. Can I take my cells and this cluster buster drug and make a hypothesis about it? Can I do my minimum experiment I've been telling you about? Thinking about what we needed for a minimum experiment, so we needed sample, treatment, an outcome measure, hypothesis. Have we got everything we need? Well, first of all, have we got a sample we can work on?
So we did a bit of fungus or something, then yes.
I think we do have a sample. We've got these cells, so they're going to take the place of our patients. So here's a sample we can work on. Do we have some kind of treatment? Okay, so we've got this cluster buster drug. So we can put this on the cells, and of course we can do this in a controlled way. We would give some of the cells nothing. We might do it in a randomised way. We might randomise the treatment across the dish.
Well, I would say, yes, I suspect what you actually do is give the control cells the same volume of whatever cluster buster is dissolved in.
That's called the vehicle. So cluster buster, if it was dissolved in water, we would just apply water to control those cells.
So otherwise you'll have slightly diluted cell medium in the others.
You do want to control all the variables as far as possible. So we have the sample and we have the treatment. What's our outcome measure? Okay, that's good. You said how long the NT2 cell line survives. So the information you're given in the first line is that these cells die in culture. So one outcome measure might be, do they survive longer if we give them this cluster buster? So that is one object, that's a scoreable outcome measure. And then what about hypothesis? Okay, how long would you like it to increase it by? You'd like it to, say, that they be improved by 25%. All right. And since this is a trial on cells, we're not putting it into animals or humans, so we can have a type hypothesis like that. All right. So we want to test the hypothesis that my drug increases the life of cells by 25%. It's important to be able to think in this kind of natural way, given minimal bits of information. Think, how can I test that? I have an idea, how can I now test that? Okay, so I've got rather a weak hypothesis. I've said it will prolong the survival of cells, so I haven't predicted that it will make them worse. But I could have said it will prolong their life by 25%. And then I might, at the end of the experiment, make an inference. An inference is, if you like, a deduction you make based on your data. And I don't want to stress inference too much, but our inference at the end of the experiment will be that clustering actually improves the survival of the cells by having an effect on amyloid. That's something we're not directly testing, but you can see that might be the basis of a later experiment.
Hypothetically, we could have started with the hypothesis that cluster buster would reduce the concentration of amyloid protein in the medium.
And that is another thing we could have tested. So as well as scoring the survival of cells, which is the easiest thing to look at, we could actually have measured the amyloid, which I told you is secreted into the medium. At this stage, you don't worry about how you're going to do that. You don't think, oh, I've got to measure amyloid, well, I don't know how that's done. You just think, what do I want to know? And then you find out how to do it. If you worry about how it's accomplished at the outset and you never do anything, in science you have to make things work. Alright, so you've come up with all the answers. You've told me that I've got cultured cells as a sample, I've got a drug treatment. Stuart made a helpful suggestion about the vehicle, which is the substance that the drug is dissolved in. Might be water, might be another solvent. I might like replicates. I don't want to just give my treatment once. I'd like to have 3 treatments, 3 repeats, and I might randomise those over the dish. Our outcome is survival time, and then of course we want to look at our data. We want to look at the improvement, if there is one, the survival, or we want to measure the amyloid in the medium. So you can see from a very simple premise, here is the cell, here is the treatment, we can make actually rather a nice experiment, provided we set this up properly and we pay attention to things like controls, and I would say being blind to the treatment. If I wanted to apply my treatment, my drug, or my control blind, how would I do that? After all, I'm standing there with the test tube. I'm putting the treatments in the cells. How can I be blind to the treatment? Do I want them to do my experiment? Would you do my experiment and say, oh, just go upstairs and dose my cells for me? You probably wouldn't. What would be another way of my being blind to the treatment?
Number them, and then write down the number of them, and
I'll remember the number. That's not the number I use.
someone else can.
Okay, get someone else to number them. So someone else could code them. So somebody else could be given, I could give you the drug, and I could give you the control, and I could ask you to code them in some way, so that it's not apparent to me what the substances are, and then I can apply them. At the end of the experiment, you can unblind me, you can then tell me what the treatments were. But what if my drug is strongly coloured? It might not have any effect. I could put dye in the control. I don't know. That's something to think about.
I mean, these things can often be virtually impossible to do. I gather there are issues now over drug trials using placebos because people aren't picking up whether they're getting the treatment because of the side effects. So, and in this case, there may be no perfect solution, because obviously if you put a dye into both, then
But it's one of those practical problems that often comes up. Can you be really blind to treatment? In that case, you might ask someone else to do it if you were satisfied they were competent and if they were part of the experiment.
or didn't care.
In a sense, yes. There are more sophisticated things you could do, but, for example, testing different drug levels. It might not work at one level, but it might work at another level. And of course, you want to know, this is what I call testing the test. Just because somebody's published a protocol that says, we know how to measure the amount of amyloid in the medium, doesn't mean that it always works. So you should be sure that you really can apply this test.
I had an example of this in a PhD student of mine who's just finished, who received from a group in Japan what they claimed was an antibody to a polysaccharide he was interested in, and he wasn't able to get it to give anything. Got in touch with a very well-respected group in the US, and they said, we've never been able to make an antibody to this polysaccharide. We haven't been able to make this antibody work either.
Okay. I think if there is time later in the module, perhaps during the How Science is Done, Stuart, Joanne and I should have a kind of round table about all the times this has happened, because I spent about 10 years after my PhD working under precisely those conditions. I was, in a sense, deceived repeatedly by collaborators, not just one man. I mean, they did it innocently, I think, but because I didn't test what they gave me, which was applying it naively, I wasted a lot of time. Simple is effective. Does anybody know about Emily Rosa? Does anybody know about therapeutic touch? Okay, Stuart, please hold your hands out like that. You are a touch therapist, and there's a screen in front of you, so you can't see me or my hands. And because you're a touch therapist, you can detect my aura. I have actually see a magnetic aura around my body, and Stuart can tell whether I'm placing my right hand or my left hand over his hand.
Close my eyes and see if it works. I saw you moving your hand.
In the experiment that was done here, the touch therapist is on this side of the screen. She can't see Emily Rosa, who's an 8-year-old girl doing a science project at school. And Emily is putting her right hand or her left hand over the therapist's hand. The therapist claims that she can detect the aura which we give off. She also claims that she can somehow manipulate your aura to cure a disease that you've got. So here's Emily, aged 8, testing this remarkable idea. And Emily randomly put her right hand or her left hand over the therapist's hand by tossing a coin. And there were 280 trials altogether. And the whole study was published in the Journal of the American Medical Association in 1998. And it was a sensation. I mean, people all over the world said, 8-year-old girl published a study debunking therapeutic touch. I have to say, I don't know how the idea of therapeutic touch strikes you in the audience. I think it's an absolutely balmy idea, but it was becoming quite influential in some American hospitals, particularly among patients who were desperate for a cure. They felt that since nothing had worked, therapeutic touch might be as good as anything. But perhaps we should ask about the ethics of providing untested treatments for people who are desperate. You know, do we really think it's helping them to give them false hope? Or do we think it might excite a powerful placebo effect? You know, perhaps patients will be cured by this kind of thing.
The placebo effect is a powerful thing, and I think it's arguable that the medical profession ought to be able to make use of it, although there are clear ethical issues involved. And so maybe passing it on to someone who genuinely believes in what they're doing is the best option, provided provided it doesn't mean they neglect something that actually works.
Yes, I think the danger of the placebo effect is deceiving people about the reasons for it. I mean, if you tell someone that you have given them a treatment that is known to work for a particular reason, and it actually has no scientific basis, then I'm uncomfortable about that. But the article's called A Close Look at Therapeutic Touch. And the abstract of this is beautifully concise, so they explain the context that therapeutic touch makers claims. The objective was to investigate this claim. They gave 280 trials in which the placement of Emily Rose's hand was determined at random. And here's the outcome measure. Was the investigator's hand above the right or the left hand? Slightly different from the way students do it. But you'd expect 50% of your chance alone. But in fact, the practitioners identified the correct hand in only 44% of cases. And you can see the practitioners were tested 10 times each. The range of correct responses was between 0 and 7. But there's no correlation between the score of the practitioner and the amount of time they have been doing it. So their conclusions were that this was of no benefit whatever and should be stopped. But that didn't require many resources, just required some careful thinking. And of course you had to get together the practitioners who actually knew the point of the experiment, and they were videoed throughout the whole exercise. So they weren't being deceived in any way that this was a debunking exercise. Can we call for a phone amnesty, please? I would like all phones to go off. And if anyone next to you has a phone, go on, just slap them around the head.
So either turn your phone off or leave.
Yes, I don't really like which.
The next one we will start on.
Please, take a minute now to do it. I don't have a phone because I know that I couldn't possibly work it. They've got so many buttons and levers and things that you have to push that you'd always be going off in the opera house and things. If your phone is too smart for you, leave it at home.
Smarter than you said, it's action.
Now this is a beehive, and I want to go back to the idea we had last week that some of the experiments are things you observe, and
Right, whoever it is, please go. Seriously? Said.
you write her name on the naughty board. I want to go back to this idea that there are some, we talked about X and Y, so X is something that you select to study. It's something that might be under your control, you might be able to manipulate it. I mean, I could survey the heights of people in the room, but I can't manipulate the height, I can collect information about them. And so there's a range of approaches to experiments. I would say that in the last experiment, well you tell me, which of these elements were present in the last experiment? The one about these cells and the effect of the drug on cell death. Okay, so I think we did do some observation. Did we collect anything from the cells?
We could have been collecting the amyloid protein, but we didn't do that in this experiment.
No, I agree with that. Did we measure or detect anything? What did we measure or detect? Okay, I think you could call this survival time a measurement. Yes. perhaps I should put detect with analyse, because that would be like Stuart's example. We might have analysed the media to see if there's any analog in it. Did we do a comparison? Okay, so we did do a comparison between a treatment and a control. Did we do a reversal or a restoring experiment?
But we're a very hard one to do in this case because you'll be doing your reversal halfway through the time course, but they're already halfway to having died. So it's
Yes, I think that you could probably think of a way of doing that experiment with these cells and this treatment, but we didn't really have that. And transpose is my name for thinking out of the box. That's where you look at your experiment and you ask a question that doesn't seem to be directly related to your conditions. The example I gave last week was that we might be looking at antibodies in the urine of cancer patients, and then the transpose experiment is to go back to, say, the pancreas, if that was the cancer we're interested in, and ask how that antibody came to be produced. We didn't do a transpose experiment here. We didn't say to ourselves, for example, what is the site, where is the place in the cell's biochemistry that the clustering is involved? Or we didn't say, if we go back to Alzheimer's patients, how is clustering coupled to amyloid secretion? Not enough scientists ask transpose experiments. They stick with their system, which works reliably. You can get data out, you can get papers. It's perfectly respectable science, but the exciting stuff is in the transpose experiments, particularly because you have to discipline your thinking. You want to propose ideas that are novel, startling, testable, but they mustn't be crazy. You mustn't have the idea that neurons travel backwards in time or something like that. So you have to have something that is, a transpose experiment has to be motivated by what is known already. So all of these elements are there, but they're not all present in all experiments. And I was going to show you an example about beehives and colony collapse disorder. I'll put this up on the Blackboard site for you to look at. But here I've chosen an X, which in the observed case is beehive populations. And then you can suggest actually what the Y would be, what would be the outcome measure. And there's a whole, if you like, hierarchy of these experiments. And I've asked, what's the if-then structure? So in the first case, it might be, if we observe the populations in these beehives, then what hypothesis might we have about that? Then we might notice that there are differences. It might be quite a weak hypothesis, but I think it would be worth knowing whether there are variations in the populations. Because if there are variable populations in these beehives, we might be able to isolate the reason why some beehive populations are collapsing. How much of our food relies on pollination? 50's at the high end, I would say, but it's 30 to 50, I would say. Would you agree with that?
Yes. I mean, you're meaning insect pollination
Yes.
as opposed to
Wood pollination.
Yes.
Stuart's the plant scientist, so we have to, he's know more about this than I do, but I'm interested in these behavioural reasons. I don't study them that. Colony collapse disorder is when all the worker bees desert the hive. We don't know why the worker bees desert, but they're the ones that actually make the honeycomb structure. They do a lot of patrolling activity during the hive. If the worker bees desert, then they're not available either to mate with the queen, and they're not actually doing the constructing work in the hive. So there's a lot of interest in finding out the reasons, and I've suggested some experiments of different types that one could do. I'll ask you to think, what's the if-then structure, what's the outcome measurement? So we'll pass over that. And then always you have to know, this is where you start to say, can I test my hypothesis? There's no point having a hypothesis that isn't testable. is your experiment feasible? And we might not know at the beginning. My advice is not to worry at the outset. But at some point, we will need to know a way of implementing the experiment that satisfies a protocol. And one source might be colleagues, other people around, but usually you have to go to the literature. And you have to have good ways of finding protocols. You know, if you've ever looked at PubMed, there are thousands of journals. You now have to use much better search terms to drill down to a few articles that can tell you one way of doing the protocol.
Starting to talk about scientific next.
Now, Stuart, do you want to talk about practical or shall we talk about this?
I think the two will connect reasonably well. So let me start on some of these things. Yes.
Okay. Well, I showed you some cells earlier, and they were growing in a dish. Cells in my freezer, you get them out and grow them. You don't always have the material ready to hand. And here's a situation where you haven't got the material. So, can you think laterally here? I'm going to tell you that it's a good presumption that heme binding proteins occur in all tissues. Heme binding proteins, where have you come across them? Red blood cell, okay, but that's not all tissues. Okay, during some aspect of respiration. If anyone says to you what happens in all tissues, think about common pathways. Without ATP, nothing would happen.
Cyanide does what it does because it
Poisons
binds.
the respiratory chain, yes. Okay, so without ATP, nothing happens. So all cells have elements of the respiratory chain, and all of the cytochromes are heme binding proteins. And it's been observed that myoglobin is abundant in muscle. What's the link between first line and second line? What's the implication there? Can you read between the lines?
Yeah, yes, I suppose that is a valid suggestion, but that we may be thinking about myoglobin as a heme binding protein, and we are talking about an active tissue, so perhaps if myoglobin is sitting that function, then, which it isn't, but it's a perfectly valid question.
Yes. So the inference I wanted you to draw was that myoglobin might be just another heme binding protein. After all, if you told me about red blood cells, what's the oxygen carrying protein there? Okay, so we've got another globin. So you might think, all right, by analogy, myoglobin is probably a heme binding protein. So that would be a good deduction. So you're now asked to design an experiment involving myoglobin as the sample, or at least as a component of the sample. And you know what a measure experiment is. You want to count some property of the system. You know what a comparison is. In the case of the NT2N cells, we have a treatment and a control. And a reverse experiment is one where, having seen an effect, you try and send it back again. Very powerful, because if you've guessed the right intervention to reverse the experiment, you have probably found something that is causal. Reverse experiments are quite hard to do, but they're high prestige experiments. So here is we need some myoglobin from somewhere, and we need to ask some questions about it. So, what materials do you need to do this experiment? You need a tissue. Okay, what might that be? Muscle. Where are we going to get some muscle from? Don't look at me. Okay, something that's recently alive, it's now dead. Where do we get that kind of thing from? Abattoirs? Or we perhaps don't have to go as far as an abattoir. Have you done the experiment with lab and liver? Okay, we didn't get it from an abattoir.
I think the liver we used for the explosions came from Tesco.
Right. So, Tesco advances the cause of science. Muscle, okay, so you've talked about animal muscle, doesn't have to be a mammal. What else could it be? That's over there.
Astonishing how many of the early biochemistry experiments on sort of muscle function and so on were lobster. And I'm sure they didn't eat them afterwards.
I'll tell you a story about that, I won't. Okay, crustaceans or just fish, teleosts. You could go to a fishmonger and you could buy a fish as a source of muscle. So, yes, you want something that's been recently, was alive until recently, so it might still have some myoglobin in it. So that might be the material. What are you going to do with this to get some myoglobin out of it?
You might think back to your cell science practice. Try to get organelles out there.
Okay, I've heard break cells down, centrifuge, fractionation. So that's right, thinking of your mitochondrial experiment, not everything you might be doing in practice is useless. This is the kind of thing that, it's a common procedure that you want to break down a tissue because it's either got some protein fraction or an organelle in it that you want to use. So that's how you go about this. So you might start with some muscle or organ, you might start with a piece of fish, or it could be lobster if it's a posh experiment. And what if you're going to do measurements, or what if you're going to do measurements, how are you going to do that on this heme binding protein? You can measure the iron content.
Yes, so that's actually quite an because most proteins aren't particularly coloured, but because of the heme in this one is, so you could actually put this one into a spectrophotometer.
And the spectrophotometry experiment could be something you could do here. So you could certainly do measurements. You could even do comparisons. What might you compare? We could. If we wanted to make a comparison between myoglobin and hemoglobin using the spectrophotometer, what would we need to know about myoglobin and hemoglobin? How much iron they take up? We could ask that. What's easier if we're using a spectrophotometer?
Right, we're going to get concentration. The thing you've maybe not done is, but if you think back to some of the lectures you've done on spectrophotometry, things don't absorb equally at all wavelengths. That's why we tell you to set it to 405 nanometers or 540 nanometers or whatever. But those are the colour of the light you're measuring. And by and large, things have a colour because they interact with some wavelengths, which stay in the material, and they bounce the others back. So, for example, that nice blue-green jumper is blue-green because it is absorbing the yellow, orange, and red wavelengths and is bouncing the others back out. So, for your sort of purpose as well. So,
how might you make a comparison experiment? Using a spectrophotometer. Different wavelengths of what? I mean, one might be to look at hemoglobin and myoglobin, but we could do a comparison experiment using the myoglobin. sample would change its spectral properties? Anything at all? Give me your wild suggestions of what we do with our sample.
My veins either are blue. They're full of blood, which I'm pretty sure should be red.
Oh, how can we change that? Have I got some potassium ferrocyanide I can inject into you? What happens when blood goes from blue to red? What's going on at the level of the hemoglobin? Okay, chemically, what kind of reactions are they? I'm not hearing the right word. Here's some oxymyoglobin, it's in the +2 state. Here's some net myoglobin in the +3 state. We can interconvert them using oxidizing and reducing reagents, but there is actually some natural interconversion in the tissue. How do we know that? What can we do in our experiment to find out how much of that there is and how much of that there isn't? We've broken down the sample and we've got the spectrophotometer. What can we do to find out something about the oxymyoglobin and net myoglobin? We've got a protein where the E iron is in the +2 state and one where it's in the +3 state. What difference might that make to the properties of the protein?
If you have the same amount of protein in your spectrophotometer, so you put it in and you blank, and then you measure at one wavelength, and then you change the setting by 5 nanometers set, blank and read again, what is that going to turn? Are you going to get the same reading across the whole wavelength? So what sort of pattern are you going to get?
Different peaks, I think. Okay. So do you think the peaks for the oxymyoglobin are going to be the same as the peaks for the net myoglobin? No, it's a good bet they're not going to be because it's a state of this heme iron. So if you knew what the peaks were, you could measure them. If you had this piece of fish, and what could you do to it that might change the outcome of this experiment? We could do that. I suppose we could let the fish go off and see if that changed the amount of oxy to net myoglobin. That would actually change things. Progressively, you would get more of this than within your tissue. There are things that you could do though in real time that don't involve waiting around. You could give it reducing agents, so you could be adding hydrosulfide to see if you could split it from one side to the other, or you could give it the oxidizing agent. What do you know about protein structure? What can you do to affect protein structures? You can heat it. Now, you could probably think of all kinds of things you could do with this specimen of fish or the protein you get out of it that would illustrate the way that the sample can be changed from one state to another. And you can measure the peaks in the spectrophotometer. And so your job, if you were asked to do this experiment, would be to find out how you're going to conduct it and what you need to know. So what do you need to know in order to do this measurement? Okay, you need to know the absorption peaks. So you would actually need to go to the literature and find that out. You know, you might be given this as part of a problem-solving exercise in the lab. You might be told, within 3 weeks, you have to design this experiment and carry it out.
Indeed.
Indeed. And so you need to find out how this system works, how you can test it, and we want you to think of some new questions you can ask about this protein to do with the way you've handled it or the agent of fish or whatever. And being able to work up these protocols and think, how do I extract protein, how do I handle it, and what do I measure, is what you need to be able to do practically, creatively as a scientist.
That's right. So I reminded you last week about this practical week which we've got coming. Have any of you had any thoughts about how you're going to go about hitting the right time we're going to give you from using the reagents we're giving you? Okay, that's good. Right, so this is one of your approaches. So you're going to work out which reagents you need to put together to give you the colour change, and then you're going to change the concentrations in order to see if this affects the time. And in this case, it's quite likely that it will, because going back to the reaction potentials in biochemistry and molecular biology, reaction rates are influenced by concentration, so this would be one approach that may well work. How are you going to establish the relationship between concentration and time? Right, so you're going to try 1 milliliter and then 2 milliliters and then 3 milliliters and so on. That's good. So your hypothesis is that the concentration of your reagents will influence the time at which the colour appears, and so you're going to control the times by changing the concentration. Is this the only approach? Do you remember the basis of the reaction? So what we have is synthesis of the triiodate anion by the hydrogen peroxide, and then the triiodate being scavenged by the ascorbic acid. And so the reaction goes round and round with no colour being produced until the ascorbic acid is used up. Good thinking. Next slide, I think, on this one. Okay, so we're going round and round until the ascorbate is used up, at which point the triiodate stays here and we get the pulse. So what else could we try? If you're making this up when you arrive in the practical, then it's not going to be a very good afternoon or morning. Some of you will have a morning as well. Not recommended. So what is the other approach you could take? That's right, we could change the concentration of the ascorbate as well. I don't strictly the quantity of concentration, but if we change the concentration, change the quantity of ascorbate, it would be used up over different periods. Okay, that's good. And so again, what's the next stage? So we've got the hypothesis that we change the quantity of ascorbate we put in, we change our time. What are we going to do next? Measure the time for what? For one quantity of ascorbate, we've got to guess. And the chap here was trying different concentrations of the reagents overall. You're saying we change the quantity of ascorbate, and we're going to just then take a guess at the giving time for colour change. But are we going to do this by? Okay, so we want 5 seconds, so we'll try this amount, and that's given us 15 seconds, so we'll try a bit lower. Are you going to try it that way, or are you going to try something a bit more systematic? That's right, so we're going to try a range of concentrations. And so what are we then going to do once we've got the data for our range of concentrations? We can do better than that. Sorry? Right. Remember I talked in the second lecture on scientific philosophy about the positivists, whose view was that all you could put on a plot of a graph was your individual data points. So that's all that you knew. And I said that's not what we wanted to do as scientists. What do you do as a scientist when you've got that data? You draw the graph, and then but you need to do something else first. Yes, you're going to do the drawing across bit, but what are you going to do? What are you going to draw to? A line of best fit. And what that line of best fit is a hypothesized mathematical relationship between x and y. That's what y equals mx plus c, or whatever it is, you might look at a straight line, is. That line is a description of that relationship. And so you're hypothesizing that this is describing the relationship between what you're changing on the x-axis and what you see on the y-axis. So we're going to do a range of measurements and times, and then we're